All right, so let's take a look at what it would be to actually train a job programmatically through the notebook. So remember we saw these samples over here, and so we saw this image classification MNIST, and this is a very popular data set for doing computer vision. And these are really great. If you want to really learn, you should really go through these and just read through them because they're probably very, very useful. I've done a lot of this before, so for me, it's not too hard to figure out, but I've actually never ran this one. So let's run it together. Again, we want to be in Jupyter Lab, so you can go here and click it there, or go to the compute if it's being a bit finicky, and just there, we'll get a tab open here, and we'll see how this goes. So what I want to do is just make sure we're back here. I'm going to click into this one, and we have a few. So there's part 1, and then we have the deploy stage. So let's look at training. I don't know if we really need to deploy, but we'll give it a read here. So in this tutorial, you train an ML model on a compute resources. You'll be training and deployment workflow via the Azure Machine Learning Service in a notebook. There's 2 parts to this. This is using the MNIST dataset and scikit-learn. And with Azure Machine Learning, probably the SDK, it's a popular data set with 70,000 grayscale images. Each image is handwritten digits of 28 times by 28 times pixels, representing numbers from 0 to 9. The goal is to create multi-class classifier to define the digits in a given image that represents. So we're going to learn a few things here, but let's just jump into it. So the first thing is that we need to import our packages. So here it does that matplotlib inlines. Just make sure that when we print things that we visually see them. We're going to need NumPy and then matplotlib itself, the Azure ML core, and then we're going to import a workspace since we'll need one there. And then I guess it just checks the version, making sure if we have the right version here. Okay, so this is 1.28.0. It's pretty common, even this in AWS, they'll have like a script in here to update it in case it is out of date. I'm surprised it didn't include it in here, but that's okay. We'll scroll on down. And by the way, we're using Python 3.6 Azure ML. If this is the future, they might retire the old one. You're using 3.8, but it should generally work if it's in their sample data set. I assume they try to maintain that, okay? So connect to a workspace. So create a workspace object from an existing workspace. Reads the file config.json. So what we'll do is go run that. I assume it's kind of like a session. And so here it says it's found our workplace. So really, it's not creating a workspace, it's just returning the existing one so that we have it as a variable here. Create an experiment. So that's pretty clear. We saw experiments in the AutoML and the designer. So we'll just hit run there. Okay. So we named it Core ML and we said experiment. I wonder if it actually created one yet. Let's go over to experiment and see if it's there. So it is there. Cool. That was fast. I thought it would like print something out, but it didn't do anything there. So create or attach an existing compute resource by using Azure Machine Compute, a managed service, data scientists, etc., yada, yada, yada. So create a compute, creation of a compute takes about 5 minutes. So let's see what it's trying to create. So we have some environment variables that it wants to load in. I'm not sure how these are getting in here. I'm not sure where environment variables are set in Jupyter, or even how they get feeded in, but apparently they're somewhere. But we have, it doesn't matter because these are defaulting. So here it says CPU cluster 0 and 4. It's going to use a standard D2 V2. That is the cheapest one that we can run. I kind of want something a little bit more powerful just for myself, just because I want this to be done a lot sooner. But again, if you don't have a lot of money, just stick with what's there, okay? So, and this is CPU cluster. So if we go here, I just want to see what our options are. Not sure why it's not showing us options here. You don't have enough quota for the following VM sizes. So it's because I'm running more than one VM right now. Yes, I've hit my quota. Okay, so like I probably would have to request for more. So I think this is the one I'm using. What's the difference here? This standard DV2 vCPUs. It's the same one, right? So request quota increase. I don't know if this is instant or not. I'd have to make a support ticket. Oh, that's going to take too long. So the thing is that because the reason is that I'm running the AutoML and the designer in the background here, trying to create all the workshops or the the follow alongs at the same time. But what I'll do is I'll just come back, and when I'm not running one of those other ones, then I will I'll come back here and continue on. But we're just here at the step. We want to create a new compute, okay? All right, so I'm back, and I freed up one of my compute instances. If I go over here now, I just have the one cluster instance for my AutoML. But what we'll do here is, again, just read through this. So this will create a CPU cluster, 0 to 4 nodes, standard D to V2. I guess we'll just stick with what is here. Just reading through here, it looks like it tries to find the compute target. It's going to provision it. It will create the cluster, call pool for minimum numbers of nodes for a specific time, so wait for completion. So we'll go ahead and hit play. And so that's going to go and create us a new cluster. So we're just going to have to wait a little while here for it to create, about 5 minutes, and I'll see you back here in a moment. All right, so the cluster started up. If we go back over here, we can see that it's confirmed. I don't know why it was so quick, but it went pretty quick there. So we're on the next section here, explore the data. So download the MNIST dataset, display some sample images. So it's just talking about it being the open dataset. The code retrieves in the file dataset object, which is a subclass of dataset. File dataset references a single or multiple files of any format in your data store. The class provides you with the ability to download or mount files to your computer by creating a reference to the data source location. Additionally, you register the dataset to your workspace for easy retrieval during training. There's a bit more how-tos, but we'll give it a good read here. So we have the open dataset, MNIST. It's kind of nice that they have that reference there. So we have a data folder. We make the directory. We are getting the dataset. We download it, and then we are registering it. So let's go ahead and run that. Not sure how fast that is. Shouldn't take too long. As it's running, we'll go over here to the left-hand side, refresh, and we'll see if it appears. Not as of yet. There it is. Go into here, maybe we explore the data. I'm not sure how it would look like, because these are all images, right? Yeah, so they're in ubyte GZ, so they're in compressed files. We're not going to be able to see within them, but they're definitely there. We know they're there. So that is now registered into our data set. Display some sample images. So load the compressed into files into NumPy, then use matplotlib. Plot 30 random images from the data set from above. Note the step requires load data function. It's included in the utils.py. This file is included in the sample folder. We have it over here. We just double click. Very simple file to load data. And we'll go ahead and run that. And it's pretty simple here. So load data, xtrain, xtest. Are we setting up our training and testing data here? It kind of looks like it because it says train and test data. That's when we usually see that kind of split. And again, it's doing a random split, so that sounds pretty good to me. Let's show some randomly chosen images. Yeah, so I guess they do set up the training data here. And then down below, we're actually showing the images. So here's some random images. Train on a remote cluster. So for this task, you submit the job to run on the remote training cluster to set up earlier. Submit your job. Create the directory, create a training script, create a script for run configuration, submit the job. So first we will create our directory. And notice it created this directory over here, because I guess it's going to put the training file in there. And so this will actually write to a training file. This makes quite a bit of sense. So if we click into here, it should now have a training file. We'll just give it a quick read, see what's going on here. So a lot of times when you create these training files, you have to do, and this is the same if you're using AWS, like when you're creating or SageMaker, you create a train file because it's part of frameworks. It's just how the frameworks work, but you'll have these arguments. So it could be like parameters to run for training, and there could be a whole sorts of ones here. Here they're loading in the training and testing data. So it's the same stuff we saw earlier when we were just viewing the data. Here it's doing a logistic regression. It's using linear, maybe a linear learning model there. It's doing multi-class on that there. And so what it's going to do is fit. So fit is actually performing the training. And then what it's going to do is make a prediction on the test set. Then we're going to get accuracy. So we're getting kind of a score. So notice that it's using accuracy as a evaluation metric, I suppose, right? And then at the end, we're going to dump the data. A lot of times like you have to save the model somewhere. So they're outputting the actual weights of the neural network and all other stuff. It's a PLK file. I don't know what that is, but if you're using like TensorFlow, you would use TensorFlow serving at the end of this. A lot of times frameworks will, like PyTorch or TensorFlow or MXNet, they'll have a serving layer. But since we're just using scikit-learn, which is very simple, it's just going to dump out that file into our outputs. This is going to probably run a container, so this outputs isn't going to necessarily be on the outputs into here. It's more like the outputs of the container. And a lot of times the container will then place this somewhere. So like it'll be saved on the container, but it'll be passed out to the register or something like that, like model registry. So anyway, we ran this, and so that generated the file. We don't want to keep on running this multiple times. I probably would just overwrite the file, so it's not a big deal. Here it says, notice how the script gets saved in the data model. So here it's saying the data folder. I guess we didn't look at that. So if we go top here, I didn't see, this is data folder. Wasn't really paying attention to where that was. I guess it looks like where more so it's loading the data in. So here it saves the data output. Anything written to this directory is automatically uploaded to your workspace. So I guess that's just how it works. So it probably will end up in here then. So util.py reference the training script to load the data set correctly and copy the file over. So we will run this to copy the file over. So I'm guessing, did it put it into here? I'm just wondering. Yeah, so it just put it in there because when it actually packages it for the container, it's going to bring that file over because it's a dependency. So configure the training job. So create a script run config, the directory that contains the script, the compute target, the training script, training file, etc. Sometimes, like in other frameworks, they'll just call them estimators, but here it's just called a script run config. So I'm just trying to see what it's doing. So scikit-learn is the dependency. Okay, sure, we'll just hit run. Okay. And then down below here, we have script run config. So it looks like we're passing our arguments. So we're saying this is our data folder, which is apparently here. We're mounting it. And then we're setting regularization to 0.5. Sometimes you'll pass in dependencies in here as well. I guess these are technically our parameters that are getting configured up here at the top, right? But sometimes you'll have dependencies if you're including other files here. And I guess that's up here, right? So see where it says environment, and then we're saying include the Azure ML defaults and the scikit-learn and stuff like that. And so then it gets passed in the env. So that makes sense to me. We haven't ran that yet because we don't see any number here. Submit the job to the cluster. So let's go ahead and do that. So it says it returns a preparing or running state as soon as the job is completed. So it's in a starting state. Monitor remote run. So in total, the first run takes 10 minutes, but the second run is as long as the dependencies in Azure ML environment don't change, the same image is reused, and hence the start time is much faster. Here's what's happening while you wait. The image creation, a Docker image is created matching the Python environment specified by the Azure ML environment. The image is built and stored in the ACR, the Azure Container Registry, associated with your workspace. Let's go take a look and see if that's the case. Because sometimes like resources aren't visible to you, so I'm just curious, do we actually see it? Okay. And yep, there it is. Okay, so they did not lie. So associated with your workspace, image creation uploading takes about 5 minutes. This stage happens once for each Python environment. Since the container is cached, subsequent runs during image creation logs are stemmed to the run history. You can monitor the image creation process using these logs, wherever those are. If the remote cluster requires more nodes to execute the run than currently available, additional nodes are added automatically. Scaling typically takes about 5 minutes. And I've seen this before where if you're in your compute here, sometimes it'll just say like scaling because it's just not enough. So running in the stage, the necessary scripts and files are sent to the compute target. Then the data stores are mounted, copied. The entry script is run. So the entry script is actually the train.py file. While the job is running, stout and the files is in the logs directory are stemmed to the run history. You can monitor the run's progress using these logs. The .outputs directory of the run is copied over to the run history in your workspace so you can access these results. You can check the progress of a running job in multiple ways. This tutorial uses the Jupyter widget. So it looks like we can run this, watch the progress. So maybe we'll run that. And so it's actually showing us the progress. That's kind of cool. I really like that. So it's just a little widget showing us all the things that it's doing. Let's go take a look and see what we can see under our experiments and our run pipeline. Because it was talking about things like outputs and things like that. So over here in the outputs and logs, I'm just curious as if this is the same thing. I'm not sure if this this tails. Yeah, it does tail. It just moves. So we can actually monitor it from here. I guess that's what it was talking about. So here we can see that it's setting up Docker. It's actually building a Docker image. And then I'm not sure, did it send it to, I mean, it's on ACR already, I think. It looks like it's just still downloading, extracting packages. So maybe it's actually running on the image now. So we'll just wait there. We pop back over here. You know, we can see probably the same information. Is it identical? Yeah, it is. So we're 3 minutes in. It's probably not that fun to watch it in real time and talk about it. So let's just wait until it's done. I'll see you back then, okay? All right, so I'm about 17 minutes in here. I'm not seeing any more movement here, so it could be that it is done. It does say if you run this next step here, it will wait for completion. Specify show output to true for a verbose log. So here, actually it did output a moment ago, so maybe it actually was done. I just ran it twice, so I'm not sure if that's going to cause me issues there. So, because I can't run the next step unless I stop this. Can I individually cancel this one here? I think I can just hit interrupt the kernel. There we go. Okay, so I think that it's done. Okay, because it's 18 minutes in, and I don't see any more logging in here. It's just not very clear. And also the logs, we just have a lot of stuff going on here. Like it's just so much. So, you know, if we were keeping pace, we probably just would have saw all these created. Yeah, so we just had a few more outputs there. But I think that it's done. Okay. It's just there's nothing definitively saying like done. Do you know what I'm saying? And then up here, it doesn't say, oh, I guess it does say that it's done. All right. So yeah, I just never ran it with this tool, so I just don't know. So I guess it does definitively say that. I already ran this, so we don't need to run that again. I just feel like we'll get stuck there. So let's take a look at the metrics. So regularization rate is 0.5. Accuracy is 9. So 9 is pretty good. The last step is train the script wrote in the output sklearn. I want to see if it's actually in our environment here. I don't think it is. So outputs is somewhere. It's in our workspace somewhere, but it's just not, we just don't, oh, it's right here. Okay. So it outputted the actual model right there. And so you can see the associated files that are ran. Okay, we'll run it. Register the work model in space so you can work with other collaborators. Sure. So if I click on that here, and we go back over to our models, it is now registered over here, okay? And so we're done part 1. I don't want to do all these other parts. Training is enough as it is, but let's just take a look at the deploy stage. Okay, so for prerequisites, we're setting up a workspace. We are loading our registered model. Okay, we register it. We have to import packages. We are going to create scoring script, deploy to an ACI model, test the model. If you want to do this, you can go through all the steps. It does talk about a confusion matrix, and that is something that can show up on the exam, is actually talking about a confusion matrix, but we do cover that in lecture content, so you generally understand what that is. But you know, I'm too tired. I don't want to run through all this, and there's not a whole lot of value other than reading through it yourself here. So I think we're all done here, okay?